I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined by my co-host Taylor Sparks. Taylor, what's new?
Life is good, man. Hey, and I'll tell you what's new around here. We actually have a new show sponsor for the Materialism Podcast, which we're excited to tell you about. In fact, if you have ordered elements online before, there's a good chance you've learned about them before. We are now sponsored. Our show is sponsored by American Elements. They are an awesome sponsor. They do a lot of providing of raw materials. So if you need high purity elements of many different varieties, we think they're a great place to check out. So you'll be hearing more about them in the future episodes coming up.
And this particular episode was sponsored by Gatan. And today we are also joined by Stuart Wright and Matt Nowell from AMETEK. Do you guys want to introduce yourselves?
Yeah, this is Stuart. I did a bachelor's degree at Brigham Young University down the road a ways.
Hey, we'll forgive you for that.
Where my dad was a professor, so that was kind of an obvious choice. Got involved in mechanical engineering there and did a bachelor's degree and a master's degree. And then the professor I did a master's degree under, Professor Brent Adams, brought me into his office one day and said, "Hey, I'm going to Yale. You want to come with me?" It wasn't on my target to go to Yale, but it worked out, and I followed him there, which meant I could continue working on the work that we were doing, which is, we'll explain later. And so I did a PhD there and then did a postdoc at Los Alamos for a few years. And then after that, we decided to commercialize the work I did for my PhD thesis. And that led to a company called SEM Laboratories, or TSL for short, which was bought by EDAX, which was bought by AMETEK.
Dude,
and now I work for Gatan and AMETEK, and who knows how many other bosses.
So you're telling me you found the back door to the Ivy Leagues,
Yeah.
and then you actually were so successful in your grad project that it turned into a company that got acquired that you're still getting to work on today.
Yeah, I still work for the same company. It's been 30 years.
Dude, the
going
freaking
on.
dream.
Yeah.
That is so cool.
Matt's much better at the dates than I am, so it's good he's here.
Well, cool intro, cool background. Matt?
So my name's Matt Nowell. I'm a proud graduate at the University of Utah.
Heck
Go
yeah.
Utes. So I went to both undergrad and graduate school here. And like Stuart, I've been involved with this for a long time. I think it's pretty rare that you have two coworkers that work together for almost 30 years. So it's been a really good relationship. I got into this because as an undergrad, I worked in the materials characterization lab here at BU.
Yeah. Whoa.
And so I'd run the SEM and
Wait, were you in our department, material science?
yeah, material science department.
Get out of town. That's so cool.
So down in I always think of it as EMRL, but
Yeah,
I think they
sure.
rename it sometimes. And so my professor at the time, Jeff Shields, he was like, I know this company. I met him at a conference in Las Vegas. They're looking for someone who knows how to run an SEM and knows material science. And so I was like, all right, I want a job, so I'll go interview. And, they attracted me saying, we have customers in London and Paris and Australia, and do you want to join? And I'm like, this sounds great. So I signed on and said, we're sending you to Cleveland. No offense, Cleveland. It took a few years before I got the cushier travel assignments, but it's been a wonderful ride watching the growth of this technique.
Matt, we're going to get a ton of bad reviews from our Cleveland.
Yeah, I'm a little worried. I'm thinking, okay, sorry,
Case
Case Western.
Well, that's awesome. Thank you guys so much for making the trip up here to talk about this. It's fun to do an episode in person. We are today going to talk about something that you are both intimately related with, which is EBSD. So EBSD, first off, what does it stand for? What is the technique and how does it work?
E is for electron, B is for backscatter. The B and the S is for backscatter, not something else. And D is for diffraction.
Okay, so what is that?
It's a technique in the scanning electron microscope. And typically when you use a scanning electron microscope, you shoot a bunch of electrons at the surface of a sample. They bounce off and you make a picture that way.
Yep.
By recording the intensities as they bounce off the surface. But with EBSD, the electrons actually penetrate into the sample a little bit, bounce around in the crystal planes within the metal or rock or whatever it is you're looking at, and then come back out and form a pattern. And these really patterns tell us a lot about the symmetry of the crystal you're looking at, the orientation of the crystal. When I say orientation, I mean like if you can imagine a crystal like steel, which is made up of very small cubes. If you had a die on the table and it was face up, that would be one orientation. If you twist it a little bit, it's another orientation. If you put it corner to corner, that's a significant orientation in steel and other metals, it turns out. And so that's what we're looking for is how these little crystals are oriented within the material, because that affects the properties and affects, or that it creates something called texture, which comes from the formation of the material, whether it be a piece of steel or of aluminum, how it's rolled or cast or 3D printed, whatever it might be. That will inform how those orientations are in the material. So that's what we're looking for.
All right. So you've got your electron going into the material, and it can either eject right back off, you visualize it, but you said it can rattle around inside. What exactly is going on, and how analogous is that to diffraction? That I guess most of our listeners are familiar with X-ray. We certainly have an episode on it. And they might be more familiar with light, right, going down,
Right.
and you get Bragg, diffraction. Is this the same thing? Is this different? What's going on there?
As I talk to friends who know nothing about materials, I often use a guardrail along the freeway because we all know what they look like.
Yeah.
And you can actually see individual grains on a guardrail. Those are actually right on the surface, and they're huge. Things we're looking at are more like, sub hair diameter in size. So they're very small. But the electrons go in and they interact with crystal planes as they rattle around. And they lose energy. And so as they come out, those different energies, some scatter coherently and some rattle around almost in a random ways and come out as noise. But the ones that come out coherently, we image, and it forms a nice pattern. I wish you should look it up on the web. There's lots of examples.
These the Kikuchi patterns?
Yeah, the Kikuchi patterns. And it's the same principle as X-ray diffraction, as light. And that's what you're seeing when you look at a guardrail in the summer. If the light's nice and bright, and you look at that guardrail, you can see the individual grains because of diffraction. Some are brighter and lighter because of that same effect. And we're just doing it with electrons instead of light.
So when I've seen these Kikuchi patterns, it's sort of like looking at a kaleidoscope. Honestly,
Yeah.
It looks like a kaleidoscope to me, like a bunch of different grains. Like there's straight lines, but they're at some crazy angles with one another. If our listeners are familiar with sort of like the X-ray diffraction, where you got intensity versus 2 theta, and there's specific peaks, and you can see where there was constructive interference and destructive interference, how on earth did you guys, as new, when this technique was born, how did you look at that and say like, oh, naturally, like that's a diffraction pattern?
Yeah, we it didn't come from us. EBSD's actually been around since 1920,
Getting close to 100 years.
almost 100 years. So the very first ones were the Kikuchi did them. The one he's named after, the Kikuchi patterns. And it's the same principles there. The different planes in the crystal produce different diffraction because of the arrangement of atoms within those planes. Some they're tightly packed, some they're weakly packed. And so that will affect the intensities. And those are the bands or the lines in the patterns that we see. And we know those correspond to crystals, and the math's been out there forever. So I didn't have to invent any math when I did it. I just had to make it work in the computer. But
Okay.
the very first one I did was with a protractor and a pencil and a compass.
No way.
And we figured out the orientation of the crystal. That took several weeks because I was
So what are you
new.
measuring? Is it the angle or like the thickness between the bands? What actually are you measuring?
So if you can imagine, I mentioned a die. So if it's face on face, we call those, the face planes we call 001.
Okay.
And then a diagonal plane would be a 110. A corner to corner, the plane that would separate those two, is a 111. And the planes are packed differently. And so the width of the bands in our patterns is affected by the packing. The angle between the different bands, I mentioned the protractor, is affected by the arrangement of a 111 compared to a 001. So you can measure that. It's so for example, that's about 55 degrees. And you can look for that.
Oh my gosh. And you actually see that
Characteristic
in the
Yeah.
in the diffractogram.
But it's
Between two 110s, so you have a 010 and a 100 is like the 1 versus 6 on a die. That would be 90 degrees, obviously. So you can look for that too.
But is this like an inverse problem where if you're looking at it, everything's relative to one another? So you have to start with assigning something, and then everything is relative to that first assignment?
Right. So the 001, we would look for that because then it's pretty easy to find. The
Okay.
others become obvious. That's really easy in cubics. I should say easy. But if you talk to a geologist who deals with, a triclinic material, it's much more complicated. And really, I don't think you could do those by hand with a pencil and a protractor. I couldn't. No way.
Right, because initially these were all labeled by hand.
Yes.
And then through, algorithmic complexity, we've been able to start to derive them computationally now.
And that formed the core of my PhD thesis, was to, one, be able to take a set of bands in a pattern, look at the angles between them, figure out what the orientation is. Then the next step was to detect those bands in the computer, so using image processing techniques.
And at the time, what was the computational speed?
I remember the first computer we had was a Silicon Graphics workstation. I don't know what happened to Silicon Graphics, but it's not a big name these days. That computer was $120,000 in, let's see, it would have been 1989, 1990, somewhere in there. And we got to where we could do one pattern every 4 seconds.
Jeez.
That was remarkable. It was, compared to the week it took me to do one pattern by hand, that was incredible. Today's systems are run on a $10,000 computer?
Yeah,
still a nice end computer. But it takes us, what are we at now?
We're about 7,000 measurements per second.
And we can actually, and that includes the camera to image these. If we were to do it without
just analysis, you mean?
Yeah. If we just had the patterns on disk, I think we could maybe get up to speeds of around 30,000 if we really pushed.
Unreal.
So part of that's computers, part of that's better algorithms, but it's come a long ways.
Okay. Let me ask another question. So I think I kind of grasped the technique and how it works a little bit. I'm curious if our listeners are like, okay, but so what? Like, why should they care about this? Why is this a piece of information that they would want to know?
That's a great question.
I have a good story to talk about it. So when I was in school, I think it was in my electronic properties class, the beginning part of the textbook when it started talking about crystallography is, they said crystallography is really important, and we're really happy crystallographers exist to do crystallography. For this class, we will assume everything is isotropic, or that your properties don't vary by orientation. And so, you think of what's the strength of my steel, or what's the seismic propagation rate in this crystal or something like that. And you don't think that it would vary by crystal direction. But in reality, a lot of your properties do vary with crystallographic orientation. So with EBSD, it's really the great tool for measuring this crystal orientation distribution to see is my crystallography random or not. So if you sometimes do something like powder metallurgy and compact something, you'll get something close to random. But most things, whether you, like Stuart mentioned, if you solidify something or you deform something, they will develop some sort of a preferred orientation. And if you want to leverage that, you can engineer better properties or selective properties by controlling that anisotropy. Of course, to be able to do that, you want to be able to measure it. And then you can measure, you can model, and you can predict, and then you can manufacture.
This was my first paper in grad school. It's still one
really?
I'm fond of, right? We had something called sinter forging. It's kind of what it sounds like. You're sintering it, so yes, it's a densification process, but you're forging it, so you're pounding on it as it's happening, which surprisingly enough actually works for some ceramics. They're not so brittle that they just get destroyed. It'll actually keep together. But as you're pounding on this thing while you're sintering it, let's say, imagine, you can't see me, but if you're pounding on it uniaxially, then if there's plate-like grains, you could imagine that those plates are going to kind of line up perpendicular to that loading force. And so what we used was just X-ray, right? We just use X-ray, and you can see that the peaks that match up with the way these grains have oriented show up really overly strong, like much stronger than the average pattern, which was collected on powder. But the peaks that are opposite to that, right, that are transverse to that, you don't see them at all. So that texturing from X-ray diffraction is the tool that we used. And then we did a sample that was untextured, a sample that was textured, and then we measured, in our case, it was thermal conductivity. And because it was a layered compound, kind of like graphite, it was not graphite, but it had a layered system in the same way that graphite does, we saw really high thermal conductivity in plane and pretty terrible out of plane. And so it was a way for us to quantify it. But I didn't use EBSD because I was a schmuck, man. We were doing X-ray, and it was way harder to quantify the degree of texturing. So when you hear people talk about texture, it's just saying the degree to which it's been oriented preferentially in some sort of way. And that can be oriented on one axis, right? In our case, we were orienting on one axis. But within that plane, these plates, they could be rotated any way you want from one another. But you could also orient on two axes, right? You can texture it in many different ways to make it almost like a quasi-single crystal, even if you want. Well, that's challenging to pull off.
Yeah, in some ways it's kind of like wood grain, right? Like there's a
Yes.
preferred
Totally.
orientation, and if your grains are then parallel to your force, the material is going to be weaker. But if they're perpendicular, you're going to have a stronger material. And in a similar way, we can design materials to kind of reflect that.
I'm sure that's the trick that many kung fu masters use when they show them chopping a piece of wood.
Oh,
100%.
definitely.
They know.
They know about anisotropy.
And I think for EBSD, it really points out one of the things you get that makes interpretation a little easier is you get a picture. A picture's worth 1,000 words, and you can see if you have a texture, you'll see one color in terms of orientation.
Well, and by picture, you're not talking about the Kikuchi patterns anymore.
Right, an orientation map.
This is now, after your software does its thing, it takes that SEM image where you saw maybe grains before, but oftentimes you see more grains that weren't immediately obvious within SEM because the way that the electrons bounce off and it gets collected is basically the same, even though there's different orientations there. But once you do the EBSD mapping, like, oh, shoot, that thing that looked like a single grain was actually multiple, and I see their difference in orientation.
Yeah, that's really true.
So just so I understand, and maybe so the audience is can understand as well. So each spot that we sample with the SEM is going to produce one of these Kikuchi patterns.
So when you do it, make an SEM image, you take a beam and you raster it across the sample, and you collect the intensity at each point, and so you kind of map that out into a picture. With the EBSD, we are also rastering, but we're moving that point. We're moving the beam in a controlled way so that at each point we collect a diffraction pattern, we analyze it, and that way we know the orientation. So when we create the image in the end, each point is a reflection of the orientation. So we use color a lot. Our images tend to be very colorful to show all these orientations. So like you said, there was a grain that looked like a single grain. So a single gray level in the SEM image turns into a red, blue, and a green part within that individual grain.
So, well, tell me about some other use cases. Like, this is interesting. Clearly strength, right? Are there other applications? I talked about thermal conductivity. Where else would people care about this technique?
So my EBSD, actually my exposure to texture was also using X-rays initially, and it was for rolling can stock, which is obviously a high volume, high money maker, high dollar thing in the United States and across the world. And so we used X-rays to try to understand that texture. And from that, if I look at a can today, it's much thinner than the cans that I had as a kid. I can smash it much easier. And that's because of getting the texture right, getting the preferred orientation right for the deep drawing process in which we form the cans. And so we wanted to look at it in even more detail in hopes of getting another level of improvement that we could get X-rays. And to do that, we not only had to know the overall bulk texture that you get from X-ray, we had to know the orientation at a given point. So we had to know this grain here has this orientation, its neighbor has this orientation. And then we can do a higher level model because now we know the orientations at a point instead of a bulk texture for the whole thing. And you can imagine other things, cracking. If a crack goes along the boundaries between the grains, it could be a function of the difference in orientation or misorientation between different grains. And so that's another place people have pursued improving materials.
So it breaks, they will do a sort of fractography. They'll look at it after the fact and be like, oh, hot dang, it was cracking along this specific. And then you can mechanistically try and understand why that certain facet or that orientation is weaker.
Yeah, and another
brittle.
good example is the high temperature superconductors. It turns out that's a very anisotropic conductivity. And so it is conductive along one direction of the crystal, but not the other. And so do the crystals line up in such a way that you can get across, different grain boundaries? Can you get transmission or conductivity across that grain boundary? So we look for percolation paths using EBSD as another thing. That was a big use early on. To be honest, I haven't heard it for a while. Maybe people do it in secret now and not telling us how they do it, but it was a big thing when we first started commercially.
I believe it.
Yeah, and I can see a lot of applications in modeling too. There's a lot of interest in looking at grain boundary evolution and the effects of grain boundaries and grain orientations in finite element models. And the hardest thing is, well, you can generate those randomly, but if you actually know what your material looks like, you can actually start to try to match that and create a digital twin, which allows you to do all sorts of other experiments.
Yeah, and the modeling is important because it tells us, if I form this material and here's the microstructure I end up with, here's what I expect in performance of the part I'm making. But going backwards with models is also important, especially in the geology and the earth sciences. So there you're trying to understand how was this rock formed, and then you can, if you know the texture now and you assume a certain random texture perhaps at the beginning, then you could use a model to say, okay, here's how I got to this microstructure. So the earth was forming in this way, or, I'm not a geologist, so I probably have the wrong word. But,
Yeah.
An earthquake formed here or whatever, it formed to create this rock at this place, this orientation. Another great one for earth sciences, one of my favorite applications is trilobites, which we have a lot of in here in Utah. You can go down to Delta and dig through
crack
the
a rock open.
Yeah, and find a trilobite. And what they found is the trilobite eyes are made of a calcite. And so that part of the fossil actually is not a fossil. It's actually the rock. The calcite was there when they formed. And the calcite is formed in a hexagonal crystal, and it is only, it's opaque. It's transparent along the c-axis and opaque normal to that. So we know they probably could only see in one direction with these eyes. So these eyes are made of all these calcite crystals. And what they found is that in some trilobites, they're all closely aligned. In other ones, they disperse from the center. They start and then they go out. So the theory is, and it makes sense to me, is that the ones that they're all aligned in the same way were deep water trilobites because they had to look up for prey or look up for food and plus whatever is going to feed on them. And the ones that go out away from a single alignment of the c-axis are probably shallow water ones because they need to look around because they're going to have prey coming in different directions and food in different directions.
Dude, that is so cool.
It is super cool. That guy does it's out of the University of Glasgow is where I first was introduced to it. But he's done earthworms,
dinosaur shells,
dinosaur eggshells. It's fascinating.
Using that same idea that the opacity, right, the transparency of light through the crystal is one in one direction, different in another. And so he will use EBSD to figure out what these different creatures have and then infer something about how they lived or how they live now.
The eggshells is another good one. So he took a look at ostrich eggshells and chicken eggshells, look at the microstructure using EBSD. They look very different. And then looked at eggs from dinosaurs, looked at their microstructures, and in certain species they're very different. So they kind of made the assumption they can use that information. I don't quite know how they make this jump, but somehow they use that to understand the temperature at which the eggs are laid, or I don't know, or hatched.
Yeah.
I'm not sure, but you can also make some assumptions about the behavior of the animal based on the eggshells that they had. Crazy stuff. Really fascinating.
Wild.
So what I know about, electrons interacting with material is you get a lot of other information out of it. Do people combine EBSD with, say, EDS?
Certainly. One of the challenges EBSD has is that I talked about the electrons go in and rattle around. For them to come back out, we typically have to put the sample at a very high tilt, typically around 70 degrees. And so that makes some challenges with other imaging modalities, even the EDS to a certain extent, because we're used to doing everything flat in the microscope. So
that's how backscatter works, right?
Yeah.
The detector's directly above it.
Right. So our EBSD detector is off to the side from this high angle. And so to match those different imaging modalities, whether it be EDS, backscatter, CL, there's a ton of different things people will do. That's a challenge to make it a one-to-one mapping, but still you can obviously get close and compare things and learn how orientation. So maybe you have hardness, for example, a micro hardness tester. That tells you about the hardness. Can I relate that to orientation with EBSD? Certainly. We have models to do that. We have pretty good understanding. So yeah, we can do things like that.
I have a master's student who just finished 2 years working on that, on a bunch of high entropy alloys. He did exactly that.
Cool.
And the way that he did to make sure that it mapped up nicely is he would put reference markers on it, right? I don't know some sort of scribe or how exactly he put these markers on the surface, but he would mark it, and that made it much easier. Or the other thing is that you can, using the nano indenter, you can put a really nice grid of indentations on it, and then you can visualize it afterwards. It's a little more difficult if you want to capture the information before and after. Like if you want to probe whether or not when you indent it, the orientation changes in some way, which I suppose is possible, maybe unlikely.
Yeah. No, it does.
Is it?
You can see the rolling at least from.
Yeah.
Like just in the deformation zone?
Even like the slopes from the indentation, you can actually get some diffraction patterns from that. So you can see the bend of the crystals from it. And it's kind of, they're pretty. They look cool.
Well, what other limitations are there with this technique?
Well, there's kind of the practical ones like speed. But today it's pretty fast. It's not like it was when we started where we would let it run over the weekend.
Yeah, I mean, I'm a golfer, so it was great. You could set up a scan and go play a round and come back and say, okay, I'm working hard today.
But today it's almost like any technique. It's minutes instead of hours.
So comparable to, say, EDS.
Yes.
Okay.
Very simple.
Dang, that's amazing.
Yeah,
that is
it
really
is really
fast.
changed.
Yeah.
Now,
Then other limitations, spatial resolution is around, it's not like the TEM, but it's still pretty good. I would probably say 20 nanometers is a ballpark. Obviously, it depends on the microscope, the sample, voltage, all those kind of things.
I mean, you can certainly push the technique. You can do EBSD in a transmission mode as well.
Yeah.
Where you can get, probably down to 2 or 3 nanometer spatial resolution, but you have to go through the trouble of making a foil.
is that not just the same as selected area diffraction, like TEM diffraction? Or
Yeah,
is it different?
It's just
the same
how
thing,
it's-
essentially?
We're acquiring, rather than collecting a diffraction pattern, with still an EBSD looking pattern. It's a Kikuchi pattern and analyzing it with the same type of algorithms.
Yeah,
so
we
you can
get
look at
like-
multiple phases instead of one at a time. You can.
Yeah.
Okay.
And you get with EBSD, you get around 60 degrees of solid angle. So solving the orientation problem with all the bands is much easier than a select area diffraction pattern. Or
Gotcha.
I shouldn't say it's easier, it's a different approach.
Yeah, it's a different approach.
Other limitations are, you got to do it in the microscope. You need to polish your samples well, more so than you would do with typical SEM imaging. But having said that, we've learned a lot that maybe you should be doing better preparation for your typical SEM imaging
For
too.
sure, you should.
I think the thing with something like EDS or SEM imaging, no matter what you put in, you'll get a signal. Whether or not it's completely relevant to what you're trying to measure is a different question, but you'll see something. With EBSD, if it's not prepared, you won't see the diffraction.
Yeah.
And so you're sort of not going any further than that.
Yeah, I remember when I was in a characterization lab, I always knew like polishing stuff, but I found these polishing pads for like 1 micron and like down to even some like nanometer size. And I was like, oh, wow, what are these for? I couldn't even imagine having to try to get like that fine of a polish.
No, Hayden, my student, was using vibratory mills, like getting it,
Oh, wow.
trying to get to that mirror finish, because he brought this exact issue up, that he was trying to get better patterns for EBSD, and it was a function of the smoothness that he was working with.
Yeah. You got to get off that deformation layers or oxidation layers. And if you have materials, that's another challenge. If you have materials that, say, oxidize quickly, or if we look at some materials that are beam sensitive, those present specific challenges that, we have ways to try to overcome them, but there are certainly challenges.
What's your collection depth? Like, it's providing you information in the top 10 microns, 15 microns, something else?
That's a really good question.
Yeah.
I mean, usually we're
I
more
would
of a
say
nanometer scale.
Yeah, I'd say nanometer
Tens
scale.
of nanometers.
Extremely shallow.
Yeah.
It's really shallow.
And that's one challenge with doing EDS together, is there is an interaction volume mismatch.
And EDS is much deeper than that.
Right.
Yeah.
Like orders of magnitude deeper.
So when we're trying to analyze like sub-micron particles with both EDS and EBSD, you'll often see an offset between the two different signals that you'll have to correct for.
Because you're working at a high tilt.
I'll say when I was doing my postdoc, I was at UCSB, and there's a lady out there, Teresa Pollock, who does the tri-beam tool.
Yep.
And it was really slick. Essentially what it's doing, as I understand it, is it's sort of like it's multiple tools in one. Yes, you can do SEM. Yes, you can do EDS. Yes, you can do EBSD, but then they do a laser ablation, and they'll blast away a layer, and then they'll do it again, and they'll blast away a layer. So what you can get is a three-dimensional reconstruction of some volume of your sample, including orientation through it. Do you guys... Do your tools do that? Do they use your tools? Like, how are you familiar with this technique?
Yeah, they use our tools. In fact, one of our newest hires in the EBSD area came out of that group. So, but yeah, they will do an EBSD scan as well on each section, or maybe not each section. Depends on what's most important.
I see. They might skip it because that's your slow step still.
Yeah, it's usually one of the slower steps. Although if you're doing EDS, it's not too different.
And you would just interpolate between the layers at that point.
Wow.
Yeah.
The reconstructions are really cool. It is a very powerful technique, and it provides you different information than, say, something like an X-ray CT, which just uses X-ray. We did just an episode on X-ray CT. Our listeners can go back and listen to it, but it's not the same information. This is more information that you're collecting at a cost, right? This is I'm guessing, slower, more arduous thing to prepare and to run, but such a cool capability.
Yeah, the 3D stuff is really cool. It's been around for a while. With the tri-beam, and then also the field or the focused ion beam, you can use that also to do serial sectioning. And then there's a few labs in the world that actually do robotic mechanical polishing, And they have a system that will pull the sample out of vacuum, polish it, put it back in. So that allows you to do
like with
larger
lapping
volume.
films.
Yes,
Holy cow!
they're really good at controlling the depth so that it's regular.
Wow.
And that allows you to do really big volume.
That's the big thing, the
How do you
volume of
know
material.
how much you've gone down?
They have a way of doing it. I'm not quite sure, but they have a way of measuring it.
I have to imagine this is really useful for additive manufactured products, just because of the layered approach already. You can get some really bizarre looking grains that if you just took a 2D cross section of, you might miss the greater detail and the 3-dimensional structure of it.
After EBSD, my professor, my PhD advisor, got into the idea of can we design microstructures, and then to get the orientations we want in. To tailor to really custom make a material to fit a given engineering application. And I wish he retired before additive manufacturing really became popular, but those who have followed on after him,
dude, it's gone nuts.
Additive manufacturing is really a way to achieve kind of those dreams.
And it is critical in additive manufacturing that you have a tool like EBSD, because the microstructures that process creates are totally crazy.
They're so different.
Massive texturing. You see all sorts of, like, all the laser parameters that you use, like the raster speed, the laser power, all these things completely impact the microstructure. And you need a tool like EBSD to see how those grains are evolving during that process.
Yeah, and you can see the gradients and controlling those gradients. That's all, the heating, all that. It's really amazing.
I think there's a really good example from Oak Ridge where they control the parameters to actually write DOE in the microstructure. So when you see it in an orientation map, it's spelled out in different colors. But it shows the idea of being able to locally tailor your microstructure for an application.
Pretty cool.
One question I have. So this all works off Bragg diffraction.
Right.
But when a lattice is strained, all of a sudden your atoms are going to be slightly displaced. Does that create noise in your Kikuchi signal?
Yes. Yeah, and that goes back to the polishing, why you have to polish so well. Because if you mechanically polish it and have too much deformation, then you're bending those crystals essentially, or moving those atoms around so that you don't get a nice coherent pattern.
But I think it's important. It's not so much noise so much as is a lack of sharpness. Your diffraction bands that you see in that pattern become more diffuse, so the edges are not as well defined. So from an analysis of that pattern point of view, the band detection is not as precise, and so your orientation precision can kind of suffer. So it can be a little bit tricky to analyze deformed materials compared to, say, a recrystallized grain.
We can do things like lower the voltage, lower the beam current to get a smaller spot so that the disturbance is smaller, and typically in a small volume than it would be over a larger volume. So that's another way to try to deal with it. But that's probably the biggest use of EBSD that we see from our customers is to study deformation.
Yeah, I did sort of a keyword search. I do it every few years of kind of download all the abstracts and things and pull out keywords from all the publications saying EBSD, and it's somewhere about 50% of the papers are referenced to some kind of deformation.
Yeah, makes sense. Well, are there cool things that AMETEK is doing going forward? Like, what's the future of EBSD look like? Obviously, faster, higher resolution. I expect that sort of stuff. Anything crazy that they're working on?
Probably the biggest thing there's been a revolution in the past 5 years, maybe a little longer, in that I mentioned using a protractor, measuring the angles between different bands to get the orientation. A new way to do this now is because we have more computer power and we've had people develop great models to simulate the diffraction pattern, is we can simulate the diffraction patterns. So now we can simulate the patterns quickly, and we can make a big dictionary of patterns at every single orientation, which is a whole nother discussion as to what constitutes that. But we can use those. We can now compare the experimental patterns to these diffraction patterns in a way that's fast enough. It used to be pretty slow, but now it's getting fast enough with GPUs and things that we can do that quickly. And that gives us, we found it helps us deal with the poorer patterns, whether it be deformation or whatever it is that's leading to a weaker, lower quality pattern. But it also helps us improve angular precision. So typically with EBSD, angular precision, we would say is about in 0.3 degree range,
a quarter
be a
degree.
ballpark. And this really gets us almost an order of magnitude better. So that helps us better understand deformation, for example. And so that's the big revolution, and we're working hard on that area to try to learn more and improve what we already have. But that's our biggest thing where we're headed right now.
Sorry, go ahead.
I was just going to say, of course, I'm going to talk about machine learning because that's what we love. But I mean, this jumps out to me as an opportunity is to take the tools that have come out of the image space where they can do upscaling in terms of resolution. You take a picture and it's a little bit blurry. There's loads of algorithms that can sharpen that up. Right. Have you considered taking an approach like that where maybe somebody collected something that had strain, bad polishing, or whatever else? It had that blurriness you're talking about, sharpening it up. And do you see an improvement, or are you just adding noise? Is there an improvement opportunity or not, do you think?
We've seen the machine learning's been applied in a couple of different ways. One is I've seen it used for, like you said, there's been a lot in the image space done with machine learning to take different imaging modalities and combine them together to get a more comprehensive picture of the microstructure. I've seen it used that way. The other way I've seen it used is, let's say you've got a material, you mentioned high
entropy alloys.
High entropy. I was going to say high energy, and I knew it was wrong. High entropy alloys, where you may not know the phases that you have in your material. And they've used the machine learning to, you have a catalog or whatever of known phases or even known symmetries, and use that to try to understand what phases you have so that then you can go back and index those to get the orientation.
Gotcha. Using
our traditional methods. But you're right. They've also used it for indexing, but that, so far, it wasn't totally convincing. So we'll have to get some more minds working on it.
I think it will. I think it's going to catch up pretty quick. I mean, I just look at what's happening in other fields similar to this, like X-ray refinement, for example. It's not there yet, but it is coming fast, dude. It's coming really fast I think to surpass it soon.
Yeah, or even in that computed tomography episode, now most of their algorithms they're using are machine learning based, and they perform significantly better at fewer samples.
Right.
Which is,
I think, another area. I mentioned the phases in the high entropy alloys, but even just in general, we find that we can often look at a sample and see where the different phases are, and we're not sure why. And so coming up with an algorithm to figure out why can be a challenge. And I think that's a real place where machine learning could help us, is solving that problem, because some phases are hard for us to differentiate crystallographically.
Oh, yeah.
And so in some cases we can use EDS to do it chemically, and it can be obvious. And for example, nickel and what other one was it?
Well, aluminum.
Aluminum,
both face-centered cubic. They should look alike, but you can just looking at them say, oh yeah, that's aluminum, that's nickel, that's copper.
But the angles, those are the same crystal structure, so it's really hard for us to do. Now, chemically, obviously, we can do it, but could we do it some other ways that machine learning could help us with when we don't have EBSD available?
Yeah.
Or EDS available?
Oh, that's cool. Other questions you got, Andrew?
I was just going to say the other big innovation we have is on the detector side, where traditionally detectors have been phosphor based. So the electrons will hit this phosphor and they'll illuminate, and we detect the light photons. We've recently developed using direct detection. So we just directly detect the electrons and use that to create an image.
So you've got a semiconductor array that's actually tuned to that right wavelength or right energy, I guess.
Yeah, correct. And so that's really improved. And the thing with those detectors is that they're essentially zero read noise. So you're able to go to much lower beam doses for things like perovskite semiconductors, things that would be really traditionally
EBSD would tear that up.
Yeah, it would just melt the sample. We can get usable diffraction patterns down to like picoamps of beam current.
So cool.
That's been pretty exciting. The direct detectors are pretty well known in the TEM, cryo-EM community for some of their protein analysis and things. And so bringing that to EBSD has been a pretty cool application space.
Do you have are there any other interesting case studies where there was a problem that nobody could figure out, and it was EBSD that maybe helped point them towards
to the
solution?
Smoking gun?
Well,
or maybe even just like aided in the design and development of an important material or class of materials?
I think one is electromigration in some of these semiconductor materials, where it's not orientation based, but it's misorientation based. What's the misorientation between grains? Because that can affect the diffusion pathways. So as some of these metallization layers are developed for semiconductors, they work to create an orientation and a grain structure that creates a grain boundary network that doesn't provide a percolation diffusion path through the material to resist electromigration. That's been one that's ongoing for years and years, but it's neat to see the progression.
I know there are some materials problems we don't know about, because, for example, we have a customer in Japan, at one of the steel companies, And we've asked and asked and asked, what do you use this for? And they're oh, it's great, we use it. But they bought something like, I don't know, probably over 20, 30 systems now for their lab. So they're measuring something that's
clearly
absolutely
integral,
critical that we haven't stumbled upon yet. So it's kind of neat to see. One of the things that's been really rewarding to me is see the variety of people that use a system that I got to admit, when I graduated from grad school, my advisor wanted to start a company. And I said, there's 5 labs that are going to do texture in the world. What's the point? He's showing my visionary, entrepreneurship here. But it's been amazing to see how many different labs, whether it be earth sciences, which I knew nothing about at the time, from steel companies to aluminum companies to universities, doing all kinds of stuff that I just never dreamed. And it's been fun because I've learned a lot more about material science than I ever would have learned if I had worked, for example, at a steel company where I'd be locked into steel. So it's been really interesting to see how many different varieties of applications there are.
If you can say, what is the most unique application you've seen?
I thought the trilobites I shared.
Oh yeah, for sure.
That was just
That's
when I
really
first
neat.
saw it.
Trilobite
I
eyeballs,
didn't see
come
that
on.
one coming. And it never dawned on me that eyeballs weren't fossils. I mean, right there, I was amazed. So it's just like, wow. So when I saw that presentation, I was floored. I couldn't believe it. I went up and talked to him afterwards, and it was really fun to learn how they'd done it.
Well, Stuart, Matt, this has been a hoot. You guys have been great guests. Thanks for coming on.
Thank you.
Anything you want to tell us about AMETEK?
No, it's been quite a ride. Starting from your kind of, I wouldn't say garage, but almost a garage.
I literally built things in the garage back in the day. So
yeah, we had soldering irons out back in the day, and it's really changed over the years. And there's been, we've traveled the world, seen all the great basements of the world, since that's where the electron microscopes are. And occasionally seen a few. I had the good fortune early on of going to Cambridge University, and it was Rutherford's lab where the SEM was I was going to work on. And I thought that was pretty cool. I was working on this old Silicon Graphics workstation in Unix and cranking away code. And I realized at the end of the week, I had not been outside and seen what Cambridge looks like. So I went out at 1 o'clock in the morning and saw Cambridge in the dark to see the different colleges. But yeah, it's been a pretty wild ride. Having been bought, starting as a startup company to a large corporation, learning a little bit about business when I am forced to, kind of avoided it over the years, and seeing how the changes that's brought to how we sell the system, what kind of customers we interact with, and how we interact with them.
Yeah, heck yeah. Okay, well, thank you guys so much for joining us. We'll wrap up here.
No, thanks for the opportunity.
Yeah, it's been fun.
This episode is brought to you by American Elements, the world's manufacturer of advanced materials. American Elements, now invent. Gatan Inc. is the world's leading manufacturer of instrumentation and software used to enhance and extend the operation and performance of electron microscopes. Gatan products, which are fully compatible with nearly all electron microscope models, include the EDAX portfolio, cover the entire range of the research process from specimen preparation and manipulation to imaging, spectroscopy, and analysis. The Gatan brand name is recognized and respected throughout the worldwide scientific community and has been synonymous with high-quality products and leading technology for more than 60 years. Gatan is headquartered in Pleasanton, California, USA. For more info, check out www.gatan.com.
Thank you as always for listening to this episode of the Materialism Podcast. If you have questions or feedback, you can send us emails at materialism.podcast@gmail.com.
Yeah, we actually love reading those. I love reading messages from fans. And also, if you would do us a huge favor, subscribe to our show. You can find us on iTunes, on Spotify. We used to be on Google Play, but it is now on YouTube. So if you look up Taylor Sparks on YouTube, you'll find them on YouTube as well there. If you leave us a review, we think that will help other people find our content, and that would be pretty rad. And then finally, you can check us out on Instagram. We have the @materialism.podcast page. You can connect with us there, leave a comment. We post lots of behind-the-scenes stuff and videos and pictures. We think you'd like it.
And lastly, we'd like to give a shout out to Alphabot and Kolobyte for making the music for the podcast. They both make a ton of really cool synthwave music, and you can check them out on Spotify and YouTube. Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.